So, we attached identity to a non-unital sister algebra and defined a new norm using the action of a tilde on A and looking at the operator norm of that, right. So, we have proved that that norm, well, first of all it is a norm and it reduces to the original norm when restricted to A. It clearly satisfies the Banach algebra norm, Banach algebra identity, and we need to show that it is actually a sister algebra with respect to this norm. So, the sister identity is what we have to prove now. Okay. So, let us start with that. So, suppose x alpha is not 0, in A tilde, we want to show the sister identity, right. So, for any epsilon positive, there exists y in A such that norm y equal to 1. Okay. So, for any epsilon positive, there exists y in A such that norm y equal to 1, and because the definition of the operator norm tells me that such that norm of x y plus alpha y. Okay. Well, what is that? That is x alpha acting on y, that gives me x y plus alpha y is greater than or equal to 1 minus epsilon times norm of x alpha, right. So, this is just if you have an operator t, then there exists vector such that norm, okay. So, maybe v t v, norm t v greater than or equal to 1 minus epsilon times norm v, right, sorry, norm t, norm t, right. So, there exists, because supremum is the norm t. So, if I take 1 minus epsilon times norm t, that is less than norm t, and so there is a vector like this. Okay. So, note that x y plus alpha y comma 0 is x comma alpha into y comma 0, right. Of course, it is the action of x comma alpha on y comma 0, right, that is why you have that. So, now let us start with that. So, maybe I go to the next page. So, 1 minus epsilon square norm of x alpha square. Okay. So, let us just show you the inequality I have here. I am taking the square of this element, right. So, that is less than or equal to norm of x y plus alpha y norm square, right. But all this, so the right hand side the norm is in A, right, and A is a sister algebra, right. So, I have the square of some element. So, that is norm of the corresponding self adjoint element, right. So, you look at a term like x star x. So, this is nothing but norm of x y plus alpha y star times x y plus alpha y. Okay. So, now I am going to write down some identity which is easy to check. It just follows from the way you multiply things. Okay. So, this is equal to y comma 0 star x alpha star x alpha y comma 0, right. So, x alpha, so if you look at this portion you will see what is happening, x alpha into y 0 is whatever is here, right, and whatever is on the left of it is the star of that element. So, if I take x alpha y 0 star, I will get y 0 star into x alpha star, right. Okay. This is less than or equal to I use the, so let me write this once more and then y 0 star, it is the same element. Okay. So, I am not changing anything right now, but it becomes easy to write down. So, look at this term as one term and I have another term here and another term here, right. I am multiplying 3 terms. So, the Banach algebra property will tell me that. So, it is y 0 star times norm of x alpha star x alpha and norm y 0. Okay. Of course, these two are same because they are equal to norm y. Remember, once you have the second coordinate to be 0, you are in A and it agrees with whatever norm is there on A. So, I will have norm y star, norm y star is norm y, A is a sister algebra, right. So, this is also norm y and norm y is equal to 1. So, norm y square is 1. Okay. So, this is just less than or equal to norm of x alpha star x alpha. Okay. So, we have this identity. So, inequality 1 minus epsilon square norm of x alpha square is less than or equal to this term for every epsilon positive, right. So, now there is no epsilon dependence on the right hand side and so I can let epsilon go to 0, I will get so everything whatever we have just done implies that norm x alpha square is less than or equal to norm x alpha star x alpha, right. This is almost the C star identity except that we want them to be equal, right. Okay. So, norm of x alpha, okay. Well, the right hand side here is less than or equal to, I can use norm x alpha star into norm x alpha which will give me norm x alpha square. Sorry, it should be more careful here. So, I can use the Banach algebra property to get x alpha star norm x alpha, right. So, the right hand side is less than or equal to that and one norm x alpha gets cancelled. So, this is less than to norm x alpha star. Okay. And of course, by symmetry because I can take one more star and so by symmetry we get the other way also, norm x alpha star is less than or equal to norm of x alpha. Okay. Hence, the star operation respects the norm, it does not change the norm, right. So, hence norm of x alpha star is equal to norm x alpha. Okay, so, this is still not quite the star identity, we have to use this once more. Okay. So, we get hence norm of x comma alpha square is less than or equal to norm of x alpha star x alpha. Here I can use the Banach algebra property, I will get. So, let me write down that norm of x alpha star norm of x alpha, but then we have just proved that the adjoint does not change the norm. So, this is norm x alpha square. Okay. So, I have something here, I have something here and then inequalities in between. So, everything should be equal, right. So, this implies norm of x alpha square which is this C star identity, norm of x alpha star x alpha. Okay. So, hence A tilde is a C star algebra. Okay. So, so we have proved that starting from a non-unital C star algebra, we can attach identity and get a C star algebra, unital C star algebra. Notice that we did not assume that A is commutative or anything. Okay. It works for both commutative and non-commutative C star algebras, even though we will soon restrict ourselves to non-commutative commutative ones. Okay. So, our aim is to prove Gelfand theorem for non-unital commutative C star algebras. Okay. So, as an exercise it is instructive to look at how this looks like for C naught of x. Okay. So, let me do this by hand to constructing the norm. So, exercise. So, let x be a non-compact locally compact T2 space, okay. And I have C0 of x. C0 of x is all continuous functions vanishing at infinity, right. So, f from x to c continuous and vanishing at infinity. So, f of infinity is 0. Okay. What is infinity? So, infinity comes from looking at the one point compactification of x. So, I can write x tilde to be x union infinity. Okay. So, this is the one point compactification of one point compactification of x, right. So, when I say f infinity, you do not need one point compactification to define z naught of x, it vanishes at infinity, meaning for every epsilon there is a compact set outside which f is less than epsilon, right, mod f is less than epsilon. But once you do the one point compactification, it is precisely all those continuous functions on x tilde which vanish at infinity that is why it is called vanishing at infinity, right. Now, what if we do the construction we have just done of the norm using the operator and so on, operator norm of multiplication on c naught of x by c x tilde, right. So, remember the a tilde, if z 0 of x is what we called a, then a tilde is identified with c of x tilde, except that the norm we defined, which was the Banach algebra norm, did not coincide with the supremum norm on a tilde, right. Here we have a natural norm which makes that into a C star algebra, and we did not get that, but that is obtained by this procedure. Okay. So, what is the operator? So, let us look at that. So, if I take f in a tilde, I want to define the norm of f, right, on a tilde. How is it defined? This is supremum over. So, you view f as an operator on a, right. So, that was my tau f, if you remember, tau, we had tau x alpha. This is from a to a. So, what is a? A is c naught of x. So, you will be looking at g going to, so g is in c naught of x, you simply multiply, right. So, supremum over, well, as a operator from a to a, how is the norm defined? You look at supremum over supremum of mod f g, right, where g belongs to a and the norm of g is less than or equal to. Okay. So, check that this is equal to supremum of mod f of x, where x belongs to x tilde now. Okay. You will get that. Okay. So, if you are not comfortable with x, you can look at the real line and see that one point compactification is a circle and do the same exercise, you will see what is happening, okay. And that is precisely what we did in the abstract settings, okay. And that is what makes it into a C star algebra. Okay. Okay. So, now we can try to develop Gelfand theorem, right. So, now suppose A is a non-unital, okay. So, non-unital commutative Banach algebra. So, I want to define the spectrum of A and try to see what the Gelfand transform is, right. But remember, since it is no unity ideal and the maximal ideal etc. Does not make sense as it is, but multiplicative linear functionals will make sense. Okay. So, define the spectrum of A, so that is going to be denoted by sigma A as usual, okay, to be the collection of non-zero. So, the definition is going to be the same in the case of unital, right. So, non-zero multiplicative linear functional. Multiplicative linear functionals on A. Okay. So, as you can't say sigma is the space of maximal ideals, because that does not make much sense. Okay. Now, let us look at sigma A. So, if I take phi in sigma A, so remember A is a non-unital commutative Banach algebra. Phi is in sigma A means phi is a multiplicative linear functional from A to C, right. It is a linear continuous linear functional plus its multiplicative, okay, and non-zero, we assume it to be non-zero. Okay. So, if phi is in sigma A, then phi has a unique extension to A tilde, okay, by So, I should give some names for extension. So, unique extension, let us call that phi tilde in sigma of A tilde. So, I am saying it is going to be multiplicative. Okay. So, any multiplicative linear functional. So, remember A is sitting inside A tilde, right. Any linear multiplicative linear functional on A has a unique extension to a multiplicative linear functional on A tilde. Okay. So, why is that? Well, how do you define that? So, we defined phi tilde. So, I need to tell you what phi tilde is on A tilde, right. So, I take x comma alpha and I should tell you what it is, and this is forced phi x plus alpha. Okay. Why is it forced? Because phi tilde is, if it is going to be multiplicative on A tilde, then identity, that is 0 1, 0 1 should go to 1. If 0 1 goes to 1, 0 alpha will have to go to alpha, right. And so, x comma alpha has to go to phi x plus alpha, right, there is no other way. Okay. So, note that phi of 0 1 or phi tilde of 0 1 is 1, and so the extension is unique. Okay, you can't have another expression at all for the extension. Okay. So, thus, and you can check that phi tilde belongs to sigma A. Okay. So, check the sigma A tilde, right, in the bigger space, check the multiplicative property, check the multiplicative property. So, if I take x alpha and y beta and multiply, it should go to the corresponding product on the other side, right. Conversely, so what we did was anything in sigma A extends to unique extension to sigma A tilde. Okay. Conversely, what happens? So, conversely if, so I will use the tilde to say that it is in the bigger space. Okay. So, if sigma tilde, if phi tilde is in sigma A tilde, okay, then phi tilde I can restrict it to the smaller space A, right. A tilde is sitting in, A is sitting inside A tilde, anything multiplicative linear functional on A tilde restricted to A gives me a multiplicative linear functional on A, but it may be 0, right. So, it could be, so let us call this phi. So, phi tilde restricted to A could be phi in sigma A or 0, right, because you are restricting to a smaller subspace, right, of codimension 1. So, it can be 0. So, it is either non-zero, in which case it is a multiplicative linear functional, or it is 0, right. Okay. So, let us see in particular. So, in particular the linear functional or the element. So, let me in particular 0 tilde. So, what is 0 tilde? 0 is the 0 map on A and it extends uniquely to a multiplicative linear functional on A tilde. Okay. So, 0 tilde is in sigma A tilde, and how is it defined? 0 tilde restricted to A is 0, that is why we call it 0 tilde, and 0 tilde on the identity is 1, right. So, on 0 1 equal to 1, right. In particular, so the if a multiplicative linear functional on A tilde, the bigger space, restricted to the smaller space A is 0, then that multiplicative linear functional is 0 tilde, right, there is no other choice. But then what is A? A is the kernel of this 0 tilde, and so the maximal ideal corresponding to 0 tilde is A. Okay. In particular, 0 tilde has kernel equal to A, right. So, this is the maximal ideal in A tilde. Remember, if you have a commutative Banach algebra with identity, maximal ideals are kernels of multiplicative linear functionals, right. In this case, A can be identified with the kernel of this particular linear functional called 0 tilde, which is 0 on A, but 1 on the identity which is outside A, and then you extend it, right. So, what did we do? So, if you look at any phi in sigma A, it extends uniquely to a phi tilde. And similarly, if I take a phi tilde in sigma a tilde, the bigger space, it restricts to either 0 or a non-zero multiplicative linear functional on A. Okay. So, hence there exists a 1-1 correspondence, 1-1 on 2 correspondence between sigma A union 0 and sigma A tilde, right. So, it is phi going to phi tilde, right. So, that is the map from sigma A union 0 to sigma A tilde, and that is a 1-1 onto correspondence. So, we have just shown that. Okay. So, that is how I identify the multiplicative linear functionals in A and A tilde. Okay. So, if phi, now we will try to prove some of the result as we have done this for Banach algebras with identity. Okay. So, if phi is in sigma A, then for x in A, modulus of phi of x. Okay. So, this is equal to modulus of phi tilde of x comma 0, right. That is how you write the extension, right. Phi tilde, phi at x is phi tilde at x comma 0 is less than or equal to. Now, you see phi tilde is a multiplicative linear functional on A tilde. A tilde is a Banach algebra, commutative Banach algebra with identity. So, any multiplicative linear functional there has norm less than or equal to 1, right. So, this is less than to norm x comma 0, and of course, this is equal to norm x, right. Notice that this works even in the C star algebra case, not just the Banach algebra case, because the C star algebra norm on A tilde reduces to the norm on A when you look at the second coordinate to be 0, right. So, whether it is the norm which is defined by sum of things or the operator and so on, you have the same result. Okay. So, which means that any non-zero linear functional is going to be in the unit ball and 0 is there. So, thus the sigma A. So, just like what we did for the commutative case, except that now you have a 0 here, right. Is the weak star closed. So, all that part is same, weak star closed subset of A1 star, right. This is the closed unit ball in A star, right. So, that follows immediately because of this inequality, and you at the most you may have 0, right. Okay. So, you can check that it is weak star closed, and so well we are trying to do exactly what we did earlier with the unit case. So, and so this space is compact and T 2, okay, because A1 star is compact and T 2. Now, the point 0 may be an isolated point. If it is isolated, then sigma is also compact, right. If it is not isolated, then if I remove 0, sigma A is going to be a non-compact, locally compact Hausdorff space. Okay. So, if 0 is not isolated, then sigma A is a non-compact, because I am removing sigma A 0 from sigma A union 0, which is compact, right. So, it becomes a non-compact, but locally compact Hausdorff space, right. And its one point compactification is sigma A union 0, right. So, if sigma A is my non-compact locally compact Hausdorff space, the 0 functional is going to be the point at infinity. Okay. So, point at infinity, right. So, if you have x which is a locally compact, non-compact Hausdorff space, you add one point infinity to it and you define x tilde to be x union infinity and define a topology. So, that x tilde is compact, right, that is the one point compactification. So, in this setup the linear functionals on A, non-zero linear functional multiplicative linear functionals on A, union 0 is going to be the one point compactification of sigma I. Okay. So, now we can define the Gelfand transform. So, I will stop with defining the Gelfand transform. Now, we can define the Gelfand transform, right, by restricting everything to A from A tilde, right. So, you take x in A, okay, then x tilde x hat. So, this is the Gelfand transform of x is going to be from sigma of A to the complex plane, right, by x tilde on acting on phi equal to, well, I look at x comma. So, this is going to be x comma 0 sorry phi x, right. So, phi x, that is the definition, which is also equal to x comma 0 hat. So, what is x comma 0? That is an element in A tilde, its Gelfand transform, because A tilde is a commutative Banach algebra with identity and we know its Gelfand transform is going to be a map from sigma of A tilde to complex, right. So, this at phi tilde, right. Okay, maybe I should write one more this step to justify this. This is phi tilde at x comma 0 and so then it is clear, right. So, x comma 0 hat at phi tilde. Okay. What does it say? So, hence if we identify, so I will stop soon, hence if we identify sigma A tilde with sigma A union 0, okay, x hat. So, that is the Gelfand transform of x in A is the restriction of x comma 0, but that is in A tilde, its Gelfand transform to, well, its Gelfand transform is actually on sigma A tilde, but sigma A tilde is sigma A union 0, right. So, if I restrict it to just sigma A, then I am going to get the Gelfand transform on A, right. Also, x comma, so this is the important point, it is easy to see, hat at 0 tilde equal to 0 tilde at x comma 0 equal to 0. Okay. So, any point in A, if I look at it as a linear functional on A tilde, right, on sorry, a continuous function on sigma A tilde, it is vanishing at the point at infinity, right, that is what this means. Hence x in A implies x tilde or x hat belongs to C0 of sigma of A. Okay. So, this is an important identification which you should understand. In the case where identity existed, we had x hat to be a continuous function on a compact Hausdorff space. Now, the compact Hausdorff space became non-compact locally compact Hausdorff space and the Gelfand transform is something which vanishes at infinity. Okay. That is because once you do the one point compactification, you have a compact Hausdorff space and you are looking at all those continuous functions vanishing at the point at infinity, right, which is 0 tilde. Okay. So, we can stop here. We will prove the Gelfand-Naimark theorem for commutative Banach algebras without identity using all this identification. Okay. So, let us stop here.